But I don't know, just kind of walk the audience through some of these things that you're saying the evidence is compounding and compounding. And I think it'd be neat to go into some of those specific evidences so that people can kind of get an idea of what you're talking about. Even though, I mean, feel free to dumb it down for me, but at the same time, I just want to give you that platform to do that as well.
Sure. Well, I'll try to give you a couple of highlights. I mean, one that's fairly recent is the recognition that of the 92 elements we see in the periodic table, all but two of them are extremely anomalous in terms of what we see in the crust of the Earth relative to what we see in rocky material elsewhere in the universe. The two that are normative are manganese and iron. Everything else is anomalous, and in some cases, extremely anomalous. So, for example, the crust of the Earth is 630 times as much thorium, 340 times as much uranium as what we see in rocky material in the rest of the universe. And it's thanks to that superabundance of uranium and thorium, our planet has had a long lasting hot core. And that hot liquid iron core being circulated has enabled our planet to have a strong magnetosphere enveloping us that allows us to be protected from deadly solar and cosmic radiation. It also prevented the atmosphere and the oceans of the Earth from being sputtered away by the particle radiation from the sun. And so, excuse me, we now have an understanding of why planet Earth has such highly anomalous elements. It also pertains to our industrial capacity. So we got 60 times less sulfur. That's what enables us to grow food. You're not going to grow any food or crops on Mars because there's way too much sulfur there, but you can on the Earth. So we're deficient by a factor of 60 times in sulfur, but we're abundant by a factor of 60 times in aluminum, 90 times in titanium, which enables us to construct aircraft that can fly all over the world. These are light metals that have very high strength. And so we have a very anomalous high abundance of these valuable elements. And there are 22 elements we see in the periodic table that are what we call vital poisons. If they exist in the crust of the Earth at too high of an abundance level, it'll kill us. But too low of an abundance level, it will also kill us. So we have to have just the right amount of molybdenum in the crust of the Earth, just the right amount of iron, just the right amount of arsenic. There's actually proteins in your body that need arsenic, but you only need a very, very tiny amount. And you get above that tiny amount, the arsenic will kill you. It has to be at just the right level. And so all 22 of these vital poisons are extremely anomalous in their abundance level here on planet Earth. And we don't see it anywhere else in the universe. So it really does look like somebody engineered it to get it just right. And astronomers again have discovered how this happened, how the early solar system formed in a gigantic cluster of about 20,000 stars that existed much closer to the center of the galaxy than the solar system exists today. And in that dense cluster of stars, the early emerging solar system got exposed to three different kinds of supernova eruption events. It got exposed to neutron stars merging together to make black holes, where these supernova and neutron star merging events happen at exactly the right time and the right distance from the Earth, so that the Earth was not destroyed, but on the other hand, got sufficiently enriched in all these elements and sufficiently depleted in elements that would be a problem. And then when all that enrichment and depletion was accomplished, we got kicked out of the birth cluster and driven to a distance twice as far away from the center of the galaxy. What kicked us out? It was a gravitational slingshot where our solar system was interfacing with four or five very massive stars that slung us out of the birth cluster. And then when we got to the ideal place for advanced life, we again engage another four or five, six massive stars that halted our movement And so we were born in the most dangerous part of our galaxy, and we ended up in the safest part of our galaxy, but only after we got enriched. Now, it's also true that our planet Earth is anomalous compared to all the other planets and asteroids we see in our solar system. And that's because our Earth formed in a way incredibly different from the other planets. The other planets formed by gravitational accretion, and our solar system began with 10 planets, not 8, 5 gas giants and 5 rocky planets. 2 of those rocky planets, the Proto-Earth and Theia, collided with one another when the Earth had oceans thousands of kilometers deep. That very deep ocean cushioned the collision so that the Earth was not destroyed. In fact, what happened, most of the mass of Theia got absorbed into the Earth, so the Earth became bigger, more massive, and denser. There was a debris cloud around the new forming Earth that condensed to make the moon. And so we have this relatively small planet orbited by a gigantic moon that stabilizes the tilt of our rotation axis. It ensured that at the just right time for human beings, we have our rotation rate slowed down to 24 hours. And that fifth gas giant planet, it got kicked out by a gravitational interaction with Jupiter and Saturn. And that gravitational interaction basically slimmed down Mars from being a planet about twice the mass of Earth down to a planet that was only 1/9 the mass of the Earth. This was called the small Mars problem. It took 20 years for astronomers to determine how did Mars get to be so small. But we now recognize if it wasn't for that transformation of Mars, there'd be no possibility for advanced life to exist on planet Earth. Now, I could give you 400 more examples just like that. But that's just one that basically shows us, hey, we live in an extraordinarily fine-tuned universe, galaxy cluster, planetary system. We're orbiting a star that's unlike any other star. One of the things I put in my book, Design to the Core, I show you the luminosity stability of our star, the sun. And right underneath it, I show you the luminosity stability of the second most stable star we found in our Milky Way galaxy. Our star, the sun, is 5 times more stable than the second best star. And if it wasn't for that extraordinary stability, we wouldn't be able to have this podcast today.
Wow. Wow, there's so many ways, so many directions I want to go with that, but that is truly remarkable. I feel like anytime that science seems to really look into something, that is the trajectory, isn't it? Towards more and more depth and complexity. It's really remarkable. I mean, I know this is not your area of expertise, but even thinking about what the cell was known to be in Darwin's day compared to what it is now. And it just seems like everything that we peer into with more and more sophisticated instruments, it just seems like there's just this limitless complexity to everything. And it truly is remarkable.
Oh, you're right. It's not just the discipline of astronomy or physics. We see it in every single scientific discipline.